of the OCaml Workshop 2016. So just before we start, I just wanted to remind you that there is a musical, electronic, functional programming performance tomorrow. So this is actually part of a relatively new workshop called FARM, which is functional art, and it's at the Beverly Hills Livehouse. It's tomorrow night, and we highly recommend it. So the last couple of years have been very eclectic performances with slightly random music, but always extremely enjoyable in unusual venues, and apparently the Beverly Hills Livehouse is no exception. So a bunch of people will probably be leaving from here after the CUFP and other workshops, and just gather there. But there is on the website a map available, and apparently it's quite a nice walk as well. So attendance recommended. So with that out of the way, I think we can get on with the final session. We have two presentations, and the first one is about generic programming in OCaml by Florent Balestrera.
Oh, it's not. Hello. Modularity and reusability are crucial notions for software development. They allow us to lower the cost of software development because we can invest time in designing modular pieces of code. The time we invest testing it or proving it correct pays when we reuse it many times. Types are also fundamental. They allow us to define tight interfaces between our modular pieces of code. Yet, sometimes they come in the way of modularity. And generic programming will somehow lessen this problem and allows us to express abstract computations beyond the limit of types. I'll give you an example. Consider computing the height of a tree. This is a very, very general notion that is common to every tree type, yet we need to define a specific instance of the height function for every specific tree type. Here I give 3 examples, and you can see the common pattern emerging. And with generic programming, we can capture the common structural computation and define only one height that can be applied to specific types. Another application of generic programming is in the removal of boilerplate code. In this function, we rename variables in an expression, and only one equation here matters, is the one in red. All the other equations are systematic, and they simply rebuild a term after recursing. Now I show you how these 2 simple examples can be defined modularly using some generic programming methods. So here I use a simple library called UniPlate based on a single generic primitive. So the construct takes a tree value and returns a list of the children together with a function that plug new children into the root node of the tree to yield a new tree. Using this primitive, we derive many useful generic functions, amongst which one to compute a paramorphism. Using this para function, we can define the generic height function, and using the transform function, we can remove the boilerplate of our renaming variables. Transform takes a function and applies it on every node of the tree in a bottom-up traversal. OCaml already has some generic primitives, although it doesn't allow to define new ones. And they're useful in most cases, but they have some drawbacks. Sometimes, mainly because they do not know about abstract types. So we have, for instance, generic equality, rely only on the, say you implement a type of sets using lists, then generic equality will be list equality and not set equality. So it breaks type abstraction. And deserialization, in addition of breaking type abstraction, also breaks type safety, because there is no thing that enforces the value we deserialize to belong to the type we want. So it's an unsafe cast, and it completely breaks the type system, and you can get segmentation faults if you're not careful. Generic programming is another case of polymorphism. So OCaml programmers are most familiar with parametric polymorphism, in which universal quantification of type variable, the values of those types cannot be inspected. So the computation is irrelevant of the actual type we have the type parameters instantiated. Another polymorphism is ad hoc, which is basically overloading. One example is overloading addition for integer, for real numbers, for complex numbers, and one equation is needed for each type. And usually ad hoc polymorphism doesn't range over all types, but over a fixed range of types for which we have given an implementation. On the other hand, parametric polymorphism ranges over all types. And generic programming is structural polymorphism. Again, types range over a universe now, and this universe gives a common representation for types. So we implement the generic function with a fixed number of equations for this common representation, and we get for free a common behavior for all types of this universe. Now I go into more detail, and I think the best way of explaining generic programming is using type theory. A universe of type is given by a type of names, of type names, U, and an indexed type that gives the meaning of these names. So given a name, we return the type of the element of this corresponding to this name. An example is the universe of finite type given by the empty type, the unit type, and finite sums and products. And so here you can see how the names are mapped to the corresponding type constructions. Now, a generic function of our universe is a dependent function. So this is not valid OCaml code. You see in red the variable x ranges over values because it's a name of a type and not a type itself. And we return a list of the elements of these types, and else is a type function. Okay, now we don't have dependent types in OCaml, but recently GADTs have been introduced. So fortunately there is an encoding of the universe using GADTs. So you see the correspondence is that a GADT fin indexed by alpha corresponds to the subset of U for which the element function is equal to alpha. So GADT allows us to fix the index for each different constructor, and the previous generic function is implemented like this in OCaml, so this is valid code. The pattern matching on the constructors of GADT fixes the index so that the right-hand side of each equation type checks. So now you see the only difference with the previous example in type theory is the type signature. It was a dependent function, and now the value which was quantified by x here doesn't even appear because it's only the index now is used. Okay, so now this is the low-level explanation of what generic programming is. If we want to implement generic programming in OCaml, we will want to capture the universe of OCaml types. But OCaml types are open. We can always define new types. So we need an extensible GADT. This is now possible, thanks to Leo White. And here is how the syntax works. So we just reflect the names of the types, not the structure. And if we want to define functions on those types, so type indexed functions, they also need to be extensible because when we add new types in our GADT, we will need to add new cases to our functions. Unfortunately, this is not a language feature, and I had to implement this as a library, so it works as a library, and I provide syntax using PPX, or I will provide syntax. It's not yet done. So this is not yet generic programming. What it is, it's ad hoc polymorphism because we can overload a function for different types. So what will make generic programming possible is the unified representation. It's called a generic view, and it has two parts. It's a type together with a type index function that maps for each OCaml type a corresponding view. So continuing the previous example of finite types, a finite type view will be a value beta fin reflecting the finite type beta together with an isomorphism between alpha and beta. An example of providing the view for some type. So here I take the Boolean type, it's a finite type, and so we associate the corresponding view as a sum of unit and unit. And now we have all the pieces we need to define a generic program. I define generic equality over finite types. All generic program usually will follow this scheme. The generic function that the user will use is a typed index function, so a ty. But the actual implementation is defined about the view. So here, alpha fin. And the top level function just calls the view and computes the generic function over this view. So here is how it works over the finite type view. And this is all we need, and now we can use equal for all the types that are in the finite type universe. Okay. Now I will talk about the design of the library. It's far from being finished. I see three parts in this library. The core is mostly done. Yeah, it's done, it's documented, and this is where all the low-level stuff happens. Type reflection, which is the extensible universe of types. Introspection is a very low-level generic view that captures precisely details of the OCaml types. So OCaml types are quite complex, and I needed all possible details of types to implement this safe deserialization. And so defining generic programs over this low-level view is not very fun. This is why a separate component of the library provides many different flavors of views, and each programmer can adapt, choose whichever view he wants for his needs. So the second part of the library, which I need to develop more, provides different views and generic combinators. And this is on the user level, so anyone can add a new view and extend the library to its needs. The last part would be PPX for syntax support and for instance, the syntax for extensible functions, and automatic support for the user types, so that the user can use the generic functions on his own types. Future work would be possibly support for modular implicits, so that the universe argument it becomes implicit, and we don't need to pass it. The main motivation for this library was to define a safe deserialization function. This is part of the secure OCaml project, and it's borrowing a lot, I mean, almost everything from Grégoire Henry's work of his PhD thesis. So now you see the types of these safe functions. They can explicitly quantify over the type that we want to deserialize. So now we can check that a value is compatible with a type and avoid a segmentation faults and other, I mean, we avoid breaking the type system basically. So this function supports almost every type in OCaml, and how it works, we reuse the low-level marshalling provided by the standard library, but we then do a check after deserialization. So we can check over cycles and over shared polymorphic sharing. We deal with abstract types and objects correctly. Extensible and polymorphic variants. The things that we cannot deal with mainly are closures, because to type check a closure, we will need to know the types of the environment, and that will require to modify the compiler. Lazy types for the same reason, because a non-evaluated lazy value is a closure. Polymorphic fields in records, we cannot check because actually we cannot represent those types. We cannot use an index of GADT which is polymorphic. And finally, existential quantification in GADTs. But we can check GADTs if they don't have existential quantification. I want to say a few things about how do we deal with abstract type in this generic programming library. To avoid breaking abstraction, the only way an abstract type is supported is if the module that exports this type also exports a public representation on which the generic functions will be run. And so this representation is defined like this. It comes with a projection and embedding, and you see that it can fail. So if we give a wrong representation that doesn't correspond to any abstract value, then it can fail. So we don't break abstraction. Can I just say a few words on comparison? I think it's useful. So OCaml has been lacking a library for. I mean, there have been recent efforts to define libraries in OCaml. I know of three. One is used in Lexify, but Lexify, it's defined by, it was designed by Alain Frisch, but I don't think it's a public library, and it uses a modification of the OCaml compiler. Another one is by Jeremy Yallop. It was published this year. It's a variation of scrap your boilerplate. It uses the type class modular implicits, and it uses meta OCaml to optimize the specialization of generic functions. The last one I know of is by Mathieu Barbin. It's called TypeRep, and it's available on Jane Street repositories, but it's not documented at all. And other than that, there are tons of Haskell libraries, and they can be compared. And if I compare my library with them, the main limitation is that there are no higher kinds in OCaml, so there are things that we cannot do very easily, but like the lifted view and fixed point view. However, there's an encoding possible, which I experimented with. It's a bit ugly, but it's possible. And so the very novel thing of my approach is that I separate the generic view from the universe, which allows, in fact, to emulate a lot of these libraries. So most of them are actually covered by or will be covered when I write the corresponding views. This is work in progress. Probably need to write a tutorial, publish it on OPAM, write more views, PPX support, support for higher kinds, modular implicit, and to do performance benchmarks. Very alpha version is available on GitHub. And the thing I want you to remember is that generic programming is very useful. It increases the expressiveness of our language. We get to define more modular programs and reuse them. The designer with generic views reconcile low and high level of detail, and you can choose which one you want for your application. And finally, this may allow us to replace built-ins with safer alternatives. Thank you very much.
We have time for a couple of questions.
Can you compare your approach with the instant generics in Haskell?
Instant generics, it's a variation of is it a variation of LI low? Sorry, can we do that offline, because I'm confused with the different names, and
there is a paper called Instant Generics Haskell Easy.
All right, so we'll discuss it afterwards. I'm sorry. So the fast answer is probably there's a generic view corresponding to instant generics that we can use in this library. The main difference with Haskell libraries is most of them use type classes to infer the representation, so that you don't have to deal with this. In our case, we give an explicit type name when we use a generic function, and the guy who defines the generic function needs to compute the generic view and recurse over the view. That's the main difference, I think.
Thanks very much. That's thanks, Peter, again.